topic of today's video is executable formats and toolchains. The reason I have to discuss executable formats alongside toolchains is because a lot of the reasons behind the decisions you'll make when choosing your toolchain will be based on which executable formats the toolchain is able to manage. And you need to be able to understand executable formats before you can make an informed decision on which toolchain and set of software tools you'll be using. And really, what is an executable format? Usually you're told when you take a course on computers, computer science, that the CPU runs binaries, or the OS loads a binary into memory and it's executed on the CPU. And this is mostly true, but it's not the full story. The truth is that usually binary files contain more than just binary code. For example, if you use Windows or Linux, you'll notice that a lot of times there's an icon in the program or the binary file, the icon that you double click. And that icon gives the brand or a logo icon that you double click on. And that's because the binary file contains data other than just the binary code for the program. In this particular example, we're talking about the brand or logo icon. That's the extra data that's inside of the binary, right? So clearly binaries don't just contain code and data, code and data. They contain other stuff. Binaries tend to contain combinations of code, data, and other resources. And a clever listener might now wonder, how does the CPU know which part of the binary file is code and which part is data? Because CPU should be executing code and not data, right? So, that's why we have executable formats. The formatting tells the OS which part of the binary file is code, which part is data, and so on. And then the OS loads the binary file into RAM, keeping the code and the data carefully separated so that the CPU never ends up executing data. And how does an executable format help the OS to direct the CPU correctly to execute only code and not data or icons or whatever? You see, an executable format wraps a binary. The binary doesn't come standalone with only code or data. It usually has a lot of these things we call descriptors. And these descriptors are bits of information encoded inside of the binary, which describe the layout of the binary file. That information tells, for example, whether the code is 32-bit or 64-bit. It tells what operating system the binary can be executed on. You know that binaries from one OS can't be executed on another OS. It tells you information about which company created the program and other such relevant information. So we've come to understand now that binaries are generally wrapped or formatted. But there are cases where binaries are not formatted at all and they don't have any format information embedded inside of them. And those binaries are called raw binaries, literally raw. They're not wrapped, they're just raw binary. And they tend to be used only at the very lowest level of the machine by programs like firmware, bootloaders, and so on. Operating systems are also low-level software, but operating systems today don't tend to be raw binaries because modern bootloaders tend to be intelligent enough to be able to understand and properly load operating system kernels packaged within formatted binaries. So, on some very old or resource-constrained computers, though, you may still find OS kernels packaged as raw binaries. But for the most part, any binary you encounter in the wild, as a user or even as a programmer, will be a formatted binary. Let's talk some more about formatted binaries. Formatted binaries generally allow binary code to take up less space on disk. You see, all the descriptors encoded into the binary allow the compiler and the operating system to work together to shrink wrap redundant data. For example, if there's a lot of data that's just nulls or zeros, right? Literally, just bytes containing the number 0 and nothing else. In many cases, you can essentially just store that as a descriptor saying, well, inside of this binary, there's 400 kilobytes of data in the binary that's all contiguous and it's all zeros. So don't bother to actually store that on disk in the binary file. But when the OS is loading the binary, it will see that descriptor and it will see that descriptor says that there are 400 kilobytes of zeros in the binary at position X. And it will just write 400 kilobytes of zeros into RAM. And, that's how the OS will basically load those 400 kilobytes by just placing them into RAM without the compiler having to store those 400 kilobytes in the binary on disk. And that saves some space on disk. Another advantage of formatted binaries is that they help you to reduce code duplication and save space in RAM, because those descriptors we talked about allow the compiler and the OS to separate code into modules which can be loaded into RAM once, but linked to and used concurrently by multiple running programs. For example, you may have seen DLL files on Windows, dynamic link libraries, or on Linux they're called SOs, shared objects. Both of these refer to the same thing, just code modules that can be linked to from multiple running programs concurrently. The common short name for these kinds of code modules is libraries, because to the operating system and to the programmer who wrote your program, it's like browsing a library full of code modules and picking the one you want. So there might be some shared library or DLL, again those are the same thing, that contains some software routines that do advanced mathematics, or they contain a physics engine for a game, or graphics library routines for transforming graphical data in buffers. Now every modern game needs all of these modules. If every program came with its own copies of these, first of all we'd waste a lot of space on disk, but secondly we'd also waste a lot of space in RAM, since the operating system is not able to tell if two copies of a file are copies of the same original file. So if each game asked the operating system to load its own copy, the OS would simply load that copy, and the same code module would end up being loaded into RAM multiple times. Instead, what operating systems do is maintain a single copy of each library module, and programs will use their executable formats descriptors to indicate that they have a dependency on a particular single library, that single library module. This way, the OS will load each module from disk into RAM only once, and then multiple programs can link to it and use it concurrently, saving space both on disk and in RAM. This process whereby programs indicate dependencies on modules is called external linking, or just linking for short. Now we know what executable formats do now. They allow descriptors to be placed into the binaries to allow for different features like saving space on disk and in RAM, and linking code modules to multiple programs concurrently, and so on. But what are the most commonly used formats in modern operating systems? There are actually many, possibly several dozens of formats. But the three that you need to know about are called PE, that's PE, ELF, and Mach-o. So what's PE? PE is used by Microsoft Windows, and that's a format used by all the .exe files you see on Windows. It stands for Portable Executable. It generally comes with the extensions .exe, .dll, .obj for objects, and so on. All of those refer to the same binary wrapping format, PE, but to different intended uses for that executable format. We'll talk about those intended uses in another video. What's ELF? ELF is Unix's binary format. It stands for the Executable Linkable Format. While the PE binary format is used with Windows, ELF is used pretty much everywhere else. It's used with Solaris, BSD, Linux, Unix, Minix, and pretty much literally everywhere. The main difference between PE and ELF is that PE binaries are created from the COFF, C-O-F-F, Common Object File Format that Microsoft had invented originally, and they have generally have functional extensions that are specific to Microsoft Windows. ELF is an open standard that was created by the open source community, and that's why most other OSs in the world are using ELF. Let's talk about the third format, Mach-o. The Macintosh operating systems like OS X, OS Panther, OS Leopard, and so on. These OSs have a kernel known as Darwin. And even though Darwin is based on a lot of Unix code, it's basically a mix of BSD and an XNU kernel. They don't tend to use the ELF format. The Mac OS, it uses what's called the Mach-o format, and that has certain very specific benefits for Mac, in the same way that the PE format has specific benefits for Windows. One of the benefits of Mach-o is that it supports multiple different CPU architectures, or CPU types, you can think of it, in one file, and these are called fat binaries. What we mean by that is that, as you probably know, most of the time you'll need to have either a 64-bit binary or 32-bit binary. And if you try to run a 64-bit binary on a 32-bit OS, the OS will fail to run it, because binaries tend to be for a particular target CPU, right? However, because macOS has a history of moving across different types of processors, it needed to support binaries that could run on multiple CPUs, right? Multiple types of CPUs. So, for example, very, very, very old Macs ran on the Motorola 68K CPU, a very, very ancient CPU that you will probably never encounter in the wild. And then they moved from that, the Motorola 68K, to the IBM PowerPC, another very ancient CPU. And now they've moved on to 64-bit Intel CPU. Macintosh programmers may want to target newer CPUs while keeping support for older CPUs. The Mach-o format enables this by basically packaging executable code for multiple different types of CPUs into one binary file. We call these fat binaries. So that's a rundown of the basic executable formats that are used contemporarily. You have the ELF format, the PE format, and the Mach-o format, and they each pertain to a different class of operating system, and OSs generally choose a particular format for specific reasons or create their own, as we've seen with Windows and Mac, using the PE and the Mach-o formats respectively. We just discussed different types of formatted executables. What about raw binaries though? We talked about this earlier. A raw binary has no descriptors. That is, it has no information encoded inside of it beyond just the basic executable code and data needed to run the program. These tend to be found at the very lowest level of the machine, like bootloaders and firmware modules and some operating systems. And what are the advantages of using a raw binary? And there's only one. They're very simple, and that's it. There are no other advantages. Raw binaries tend to be very bloated and very large. As the program becomes more complex, it becomes less simple to encode redundant data. Like we talked earlier about shrink wrapping a large stretch of data that has the same value, usually zeros. This can't be done with a raw binary because there are no descriptors. You'd have to literally encode 400 kilobytes of zeros, in that case, inside of the binary file because, well, there are no descriptors to shrink wrap those 400 kilobytes of zeros, and that's a lot of space on disk. That begins to add up as you have more and more, you have a larger program where you have more raw binaries on disk. Raw binaries cannot be linked to other code modules like formatted binaries can. Raw binaries don't have the descriptors to tell the operating system that they have a dependency on another library code module. They must package all of the code that they need to execute within themselves. So if you were to package a modern game as a raw binary, first of all, the binary itself would probably be several hundred megabytes or even gigabytes large. And I'm not talking about the other accompanying files that would support the game. I'm talking about the binary itself, that binary that you double click to load the game, that single binary file. Because it has to have packaged inside of itself all of the relevant libraries it needs to transform the graphical data, to run the physics engine, to process the audio buffers, to expand the JPEGs and the different textures that it runs with, and all these different things. So, I mean, why are raw binaries used at all? Why would firmware or bootloaders want to use them if they're so horrible? Well, raw binaries always begin executing at the very first byte in the file, and because the lower levels of the machine are less intelligent, raw binaries make it easy for them to execute code. All they need to do is just point the CPU at the first byte in the file and everything just works. And that's a very basic rundown of binary formats.